Hello everyone, JCE Connect. I welcome you all for this lecture. In this particular lecture, I'll be taking a second case, that is jet striking symmetrical curved vane tangentially at one of the tips. That is a stationary case only. We had the first case, that is a jet striking symmetrical curved vane at the center. So we have solved in previous lecture, and we have got the equation also for that one. So in this particular lecture, I'll be taking the jet striking symmetrical curved vane tangentially at one of the tips. Okay, so in this case a curved vane is been considered, and that too stationary. This is fixed, and this curved vane is symmetrical about x-axis. So this is the x-axis and this is the y-axis. So this vane is fixed, symmetrical about the curved vane, and the jet is striking tangentially at one of the tip. So these are called as a tip of vane or tip of plate. These are called as a tips. Okay, so and here the water is flowing through a pipe. So this is water is flowing through a pipe. Again, for a pipe, a nozzle is been fitted at the end. This is the nozzle. Just to increase the kinetic energy of the liquid, a nozzle is been fitted here. And when the liquid comes out from the nozzle, it will be coming with a high velocity jet. So this jet will be having a diameter d, jet of dia d. So this will be having a jet of dia d, which is striking at one of the tips tangentially. So after striking, the water will glide over the surface, then it will exit. Okay, but this is a symmetrical case. Again, as I said, symmetrical means this plate is kept symmetrical about the x-axis. Then whatever the angle it is making, the jet while entering, see whatever the angle it is making, so this is the direction of jet, and the jet is coming out of the nozzle with a velocity v. This velocity is v here, and if I draw it horizontally here, so it is making an angle of theta here. And when I resolve this velocity v into two components, this is the velocity v, and I'll resolve this one. So if this is one component, this is another component. So this component is v cos theta, and this component will be v sin theta. And after striking a jet, the jet will striking the vane at one of the tip tangentially, then the water starts gliding over the surface like this, then it exits like this. It exits with the same velocity v. Then here also it makes or it exits with some angle. That angle is theta here, and this component again becomes v cos theta, and this component will be v sin theta. And while entering, it making an angle of theta. If this is theta, which is entering tangentially, if I draw a tangent like this, so this also angle theta. If this is theta, this is also theta, and this angle is 180 minus theta. This is called angle of deflection. Angle of deflection. Okay, so now in this case we have to calculate what is the force exerting by the jet on the vane in x direction as well as in y direction when the jet striking tangentially at one of the tip, keeping the vane, that is curved vane, symmetrical about the x-axis. So again, symmetrical, whatever angle with which the jet is entering into the vane, with same angle it is exiting at outlet. Okay, here the same angle. So inlet angle as well as outlet angle will be same here. Okay, so in this case let us consider a jet of diameter d coming out of the nozzle with a velocity v strikes symmetrically. It is striking a symmetrical curved vane, that is a symmetrical curved vane at one of the tips. And here also you have to make an assumption that this inner surface of the vane is a very smooth, and the moment the jet enters into the curved vane, it will glide over the surface, then it exits without any energy loss, without any frictional loss. Okay, here, so with what velocity is entering, with the same velocity it is exiting. Okay, that is the assumption you have to make. Then let us take the v, that v represents the velocity of the jet, and the theta represents the angle made by the jet with x-axis. That is angle made by the jet with x-axis at inlet as well as at outlet. So this theta is the angle made by the jet with horizontal at inlet as well as at outlet, and v is the velocity of the jet entering into the vane and exiting with the same velocity, because we have assumed this surface is very smooth. Okay, so after this, so let us apply impulse momentum equation as usual, you know. So for solving impact of jet problems, we have to use one theorem, that is impulse momentum theorem. That impulse momentum equation we have to use, and about this equation you all know. And this, why it is called as impulse momentum equation, that is the force which is acting in a very short interval of time by the jet on the vane, and because of that we have to use impulse momentum principle. So the force exerted by the jet in the direction of x, we want the force in the direction of jet, even though the jet is striking tangentially at one of the tip by making an angle of theta with horizontal, but we need to resolve, or we need to calculate the force in x direction and force in y direction. Finally we have to get the resultant of force, that is a resultant of force by the jet on the vane. Then here I am applying the impulse momentum equation. So we know the impulse momentum equation, that is fx. Why I am taking fx here? Because we want force in x direction here. The x direction force can be calculated, that is rate of change of momentum in the direction of jet. So since the force is applying in x direction, hence the momentum also we have to take in x direction. Okay, then what is the momentum? That is a mass into velocity. Since we are taking with respect to time, then it becomes a mass flow rate into change in velocity. So here the mass of the fluid coming out of the nozzle, whatever the mass of fluid coming out of the nozzle, that remains same. Only the change what we get here, velocity, the velocity get changes. So that velocity can be taken initial velocity minus final velocity. This mass flow rate is rho a v, that is rho is the density of the liquid, a is the area of the jet, and v is the velocity of the jet, into initial velocity minus final velocity. Now I can write this one again. I can write rho a v. So I'll write what I'll write, v1x minus I'll take v2x. So what v1x represents? v1x represents initial velocity of jet in x direction, initial velocity of jet in x direction, and what v2x represents? Final velocity of jet in x direction. Okay, so we want force in x direction, you have to take the velocity in x direction as well as that is initial velocity in x direction as well as final velocity in x direction. So now referring to figure, so you have to take what is v1x in this case. So here what is v1x? The v1x will be what? V cos theta. This one, because we want velocity in x direction. This is the velocity. This is the velocity. It is making an angle of theta. But when I resolve this velocity, this is the resultant velocity. When I resolve, I'll get a two components. One in the y direction, other one is the x direction. But I want velocity in x direction, that is v1x, v cos theta. Then what is v2x? v2x, again I'll get minus v cos theta. So because it is opposite to the direction of jet, so I'll get a minus v cos theta, that is final velocity. Then if I substitute here, what I get here? V cos theta minus of minus v cos theta. Then simplify this one, I'll get rho a v. This is v cos theta plus v cos theta. Take v out, rho a v square. That is, I'll get this one is 2. This v cos theta plus v cos theta becomes 2 cos theta. Then finally answer is 2 rho a v square cos theta. This is Fx, force exerting by the jet in x direction. This is the formula. Similarly in y direction, that is force exerted by the jet in y direction. So how I can write? Fy equal to, again, mass flow rate, mass by mass per second into initial velocity minus final velocity. Mass flow rate, that is mass by time. You can write it as a time, mass by time. That is written as rho a v. So initial velocity in y direction. So again referring to figure, so I can take v1y y direction, that is v sin theta, and v2y, I'll get v sin theta. So initial velocity in y direction, final velocity in y direction. So what you get here, I'll write here v1y minus v2y. So v1y, initial velocity in y direction, that is v sin theta, and v2y, v sin theta. What I get? Rho a v sin theta minus v sin theta. So this 0, the answer will be 0. This get cancels, you will get answer 0. So there is no force exerting by the jet on vane in y direction. Okay, so only the force is exerting in x direction. So finally the resultant can be written as root of fx square plus fy square. And what is the direction of the resultant? Tan inverse of fy by fx can be written. Okay, so this is the answer. I hope you understood this derivation. This is very important for the examination point of view. So here the jet is striking a symmetrical curved vane, but the vane is kept stationary and jet is striking tangentially at one of the tips. First you draw the vane, then allow the jet to enter into the vane tangentially. Okay, it is entering tangentially by making an angle of theta. So sometimes if theta is 0 means, suppose if theta is 0, so this is the vane. So when theta becomes 0, so it will enter like this, tangentially only. It will enter tangentially. So this is also correct. That time V, this is V. Okay. So practice this derivation. I hope you understood this second case. Okay, in third case, what we take? So third case, we'll take again the curved vane, striking tangentially at one of the tip, but the vane is kept unsymmetrically. Means the jet will entering with some angle and it will exit with some other angle. That is unsymmetrical case. Means the vane is not symmetrical about the x-axis. It's not symmetrical about the x-axis. That is not mirror image of one another. If you draw a center line here, so this vane is not symmetrical about the x-axis. So how we can identify? The jet will enter with some angle and it will exit with some other angle. That is the third case. The jet striking unsymmetrical curved vane tangentially at one of the tip. So that we'll see in the next part of this lecture. Thank you.